So we have looked at some methods of converting a unit hydrograph which is for a given duration, let's say 4-hour duration, to some other unit hydrograph which is a duration multiple of 4 hours. So we have seen that we can use the principle of superposition and add, let's say we want an 8-hour unit hydrograph, we can add 2 4-hour rains, find out the total hydrograph, which is because of these 2 rains of 4 hours duration each, and intensity of 1/4 centimeter per hour, because that is the intensity of the 4-hour unit hydrograph. Now for the total 8-hour, we have 2 centimeters of rain. So after we add these 2 hydrographs up, we have to divide the ordinates by 2, and then we will get the unit hydrograph for 8-hour duration. For durations which are not even multiples of 4 hours or the given hydrograph duration, we have seen that an S curve can be developed, and then any required duration hydrograph can be developed by shifting the S curve by that particular amount and then dividing the resulting hydrograph by appropriate amount. So we will look at the example where we are given a 4-hour unit hydrograph and we want to obtain a 2-hour unit hydrograph. So let's look at this table which shows the 4-hour unit hydrograph at different times. You can notice here that the intervals are not regular. So initially we have data at 2-hour intervals, and then we have data at 4-hour intervals. So it makes the computations a little bit trickier. If we have equal space data, then the calculations are a little easier, but for this also we can use the method of S hydrograph. The S curve is nothing but addition of a large number of unit hydrographs. So if we have this 4-hour unit hydrograph, let's assume that this is due to the first rain of 4 hours, then we shift it by 4 hours. So all these ordinates get shifted by 4 hours. So this 0 corresponds to 0 hour here, but 4 hour for the second curve. Similarly, for 6 we will take the value which corresponds to 2. So any value here, for example this 24 will correspond to 20, 20 will correspond to 16, and 16 will correspond to 12. So all the ordinates here are shifted by an amount of 4 hours. That means if we have the first rain 4-hour, intensity 1/4 centimeter per hour, then the first column gives the ordinate because of that. Then we have another rain of 4-hour, same intensity, but now starting at t equal to 4. So we have shifted everything by 4 hours. So the second column, this column represents the hydrograph due to this rain. And similarly we can have a third rain which represents this, and so on. So we add a lot of these hydrographs together. So for the first one 0 and 2 and then 5. So these 3 ordinates remain the same as the 4-hour UH because no other rain has contributed yet. But when you go to the 6 hours, then we have an ordinate of 7.5 hours due to the first rain and 2 for the second rain. So 7.5 plus 2 gives us 9.5 meter cube per second as the ordinate of the S curve. So ultimately it will reach a constant value 22.2. The plot is shown here. So this value and as we have discussed already that this corresponds to a rain of 1/4 centimeter per hour occurring continuously over the catchment if the area is a kilometer square. Then we have seen that we can relate this Q as 2.78 A, where A is the area in kilometer square, and this 2.78 comes because of using the units of kilometer square and hours. So this will be in hours. So this 2.78 comes because of conversion from kilometer square per hour or centimeter into kilometer square per hour to meter cube per second. So once we get this S curve, you can notice here that this is not a very smooth curve, and what we would then do is do some kind of a smoothing to get a smooth S curve hydrograph, and we will use this smooth curve to obtain the unit hydrograph for any other duration. So for example, here we have listed the ordinates which are after smoothing the curve, and then we lag it by the required amount. In this case we want a 2-hour hydrograph, so we lag is 2 hours. So that means that once we get this smooth S curve from this figure, we get the ordinates and then we shift everything by 2 hours. So we can see here everything is shifted by 2 hours. So initially we don't have any problem till 14 goes to 16. Once we go to 20, however, if the data is unequally spaced, we have a problem that we don't have any value corresponding to 18. So in that case we can take the mean of these and put it here. Or when we are smoothing the curve, we can take ordinates at every 2 hours or every 4 hours, whatever we desire. In this case we could have taken ordinates at every 2 hours and written it in the table, but even if we don't have regular spacing of data, we can do some kind of interpolation to obtain these ordinates. Once we lag it, then we take the difference. Now the difference of these, what it means is that if we lag the S curve by 2 hours, the difference of these ordinates, as we have seen, the first S curve is because of a rain which is of infinite duration, intensity 1/4 centimeter per hour. The second curve is due to a similar rain but starting at 2 hours, and intensity same 1/4 centimeter per hour. So this means that the difference of these two, the ordinate shown here, will be because of a rain which is 2-hour duration and intensity of 1/4 centimeter per hour. Now since we want unit hydrograph for 2 hours, our range should correspond to 2-hour duration and 1/2 centimeter per hour intensity. Comparing these two, we see that whatever ordinate we get here has to be multiplied by 2 because the ordinate corresponds to 1/4 and we want intensity of 0.5 centimeter per hour. So that's why when we take the difference, we multiply it by 2, and this way we can get the ordinate of the 2-hour unit hydrograph. So in this case it's quite straightforward. The difference of these two into 2 will give us 8. Difference of these two is 4 times 2 will give us 8. So any point we can take difference of these two into 2 will give us 0.8. So this 2-hour unit hydrograph which we can obtain from the S curve can be plotted, and in this case it looks like this. The peak occurs at about 8. In this case these 2 points are, as can be seen from this table, 8, and therefore when we draw the hydrograph it goes a little more than 8. We can again draw a smooth curve, so some curve like this may be better suited for the hydrograph. So any duration other than the multiple of the given hydrograph duration, we can obtain the unit hydrograph using the S curve, and this can be used to obtain even for higher durations. For example, if we want 6-hour duration, we can still do the same thing. But suppose we want 6-hour duration, we may again do it by first obtaining a 2-hour unit hydrograph and then using the superposition, superposing it 3 times to get 6-hour unit hydrograph. So it depends on what we find more convenient. But S curve can be used to derive unit hydrographs for any duration, which is not a multiple of the given duration. So we have looked at if unit hydrograph for one duration is available, how to get unit hydrograph for any other duration. But now the question is how to get unit hydrograph for a particular duration. So we will look at some methods of obtaining, let's say, a 4-hour unit hydrograph. So in this case, suppose we have a catchment which is of area 60 km square. So let's see, this is our catchment, and let's say that at this point A we have a gauging station at which the stream flow record is available to us. And let's also say that there is a 4-hour rain which occurs in the catchment of some intensity which may not be equal to 1/4 centimeter per hour. In this case, the rainfall which occurs on the catchment has an intensity of 5 millimeters per hour. So this implies that total effective rain is 4 into 5 millimeter. So this is 2 centimeter. And because of this rain, which again there are some assumptions which we have to make. For example, we will assume that this 4-hour effective rain occurs uniformly over the entire catchment of 60 km square area. So if it occurs uniformly over the entire area and we measure the discharge at point A, this is the table which gives the values of Q at different times. So at 0 hours we start. Now this is 0, this is the direct runoff hydrograph, DRH. So we have already separated the base flow, that's why it is starting from 0. The actual stream flow at A at the beginning of the rainfall may be some other value which comes from the base flow. So the DRH starts from 0 and these are the ordinates at different times. So in this case we have taken data at equal spacing of 2 hours. So every 2 hours we have measured the discharge at the point A and listed that in this table. A plot of this DRH is given here. So we can see that it starts from 0, 6, 18, 30. So 30 is the peak discharge. So we have 6, 18, 30, and therefore this hydrograph, this is DRH due to 2 centimeter rain. Assumptions of course are that it is uniformly occurring over the entire area of 60 km square. Once we have this DRH, finding out the unit hydrograph is quite straightforward because this is due to 2 centimeters of rain and we want unit hydrograph which corresponds to 1 centimeter of rain. So UH corresponds to 1 centimeter of rain. This is already available to us for 2 centimeter of rain. So we divide each ordinate by 2 and we will get the UH ordinate. So this is nothing but DRH divided by 2. So the peak instead of 30 becomes 15. So this is a very straightforward way of obtaining the unit hydrograph, but the condition is that a rainfall of almost uniform intensity and for that particular duration should be available. So in this case we say that 4-hour unit hydrograph can be obtained if a 4-hour rain is available and corresponding discharge is also available. So the 4-hour unit hydrograph looks like this. This is similar to the DRH. Simply dividing by 2 all the ordinates, we get this unit hydrograph. Now most of the times the rainfall, constant intensity rainfall for 4 hours may not be available. For example, we may have a rainfall which may be a different duration. It may be like 6 hours or 2 hours. In that case, we can derive a unit hydrograph for 2 hours or 6 hours and then get 4-hour unit hydrograph from that hydrograph. Now, sometimes a uniform intensity rainfall may not be available. Sometimes the intensity may be varying. For example, we may have an ERH, effective rainfall hydrograph, as let's say 2 different 4-hour rains of varying intensity. For example, we may have intensity like this, then we may have intensity like this. So in this case, how to obtain the 4-hour UH? So this is the case which we will discuss now. Suppose we are given that a rainfall of 5 millimeter per hour occurs for 4 hours, and then it is followed by another rainfall which is of uniform intensity but a different intensity, 10 millimeter per hour, again for 4 hours. So the problem is that if we know the direct runoff hydrograph DRH, which corresponds to a combination of these two. So we have 5 millimeter per hour and then 10 millimeter per hour for 4 hours. 4 hours. This is the ERH. So that means we have 2 centimeter rainfall here, 4 into 5 millimeter, and then we have another 4 centimeter of rainfall here because this is 1 centimeter per hour for 4 hours. So in total we have a 6 centimeter of rainfall over the area, which is 60 kilometers square, and the DRH which we have measured at A is given by these values, where the peak value, as can be seen here, occurs at 10 hours and is equal to about 77 meter cube per second. This DRH is plotted and can be seen in this figure. This, if you see this curve, up to 4 hours there will be no change compared to the 4-hour UH, but then since another rainfall occurs, we will have this variation, which means that we will have a sum of rainfall ordinate or the DRH ordinate. Suppose we are looking at 6 hours. This 42 corresponds to the 6-hour value for the first rain and the 2-hour value for the second rain, because the second rain has started after 4 hours. So that's why this curve ordinates up to 4 hours. There is no problem, it's only because of a single rain, so we can use the 4-hour UH ordinate directly. But after that we will have a combination of the first 4-hour 5 millimeter per hour rain, and then we have some ordinate which comes from the second 4-hour 1 centimeter per hour rain. Not the ordinates at the same time, but they are shifted. So using this DRH, if we want to evaluate the unit hydrograph, we will have to do an analysis like this. Suppose the ordinate of the 4-hour unit hydrographs are U1, U2, U3. So T 0, then 2, 4, 6, 8, like this. And suppose the 4-hour UH ordinates are U1, U2, U3, like this. So the DRH ordinate, since the first rainfall is of total 2 centimeter effective rain, 2 U1 should give us the direct runoff because of this rain. So D1, this represents the DRH ordinates, D1, D2, D3, and so on. So what it tells us that if we have unit hydrograph for 4 hours with ordinate U1, the direct runoff will be 2 times U1 because the rainfall is 2 centimeter, compared to 1 centimeter for the UH. Now D1 is given to us. D1 is 6, as can be seen from this table. So D, which is the direct runoff hydrograph ordinate at 2 hours, is equal to 6, and therefore it gives us a very straightforward way of computing U1. And U1 will come out to be 3 from this equation. Similarly, at 4 hours, since the second rain has not yet started, we have a similar equation which tells us that 2U2 will be equal to D2. Since D2 is given as 18, U2 will be obtained as 9. Now, when we go to the next time, which is 6 hours, then we have a combination of ordinates coming from both the first and the second rain. For the first rain, the ordinate will be U3, which will be at 6 hours and multiplied by 2. For the second rain, the ordinate will be U1, which corresponds to 2 hours. Because we are computing at 6 hours, means the second rain has started 2 hours before that time. Therefore, we have to take U1 and multiply it by 4, because the second rain total rainfall is 4 centimeter. So 2U3 plus 4U1, this should give us the direct runoff ordinate at the third point, which is 6 hours, and this is known to us 42 from the table of DRH. So this 42 will be equal to the sum of 2U3 and 4U1. Now U1 is already known to us because of the first equation. U1 is known to us as 3, and therefore we can solve this equation and get this 15, because 4U1 will be 12. So 42 minus 12 divided by 2 will give us U3. So we get an ordinate U3 equal to 15. Same way, we can write 2U4 plus 4U2 equal to D4, which is 58, giving us U4 of 11. So in this way, from a complex storm, the condition is that all the storms should be of the same duration, 4 hours in this case. There can be multiple storms, not only 2, there can be 3, 4, any number of storms, provided they are all of the same duration. We can use this. The only thing is that after a few hours, we will have sum of 3 different ordinates. So here we had 2 ordinates because there were only 2 rains of 4 hour duration. If we have 3, then after 8 hours, so 0 to 4, we will have a single ordinate. 6 to 8, then we will have 2, and then after that we will have 3 ordinates, sum of 3 ordinates. But again, sequentially we can obtain all the values in this way. The problem with this is that if there is some small error in the data, it gets magnified because we are doing it sequentially. So any small error in one of the ordinates will get magnified as we move away, and sometimes it may happen that the values here get negative. So, or some oscillations may be there. In this case, since we have taken exact data, this resulting unit hydrograph which we have obtained by computing this U1, U2, U3 and so on, it turns out to be quite smooth. So we say that this is a 4 hour UH which we have derived based on the direct runoff hydrograph corresponding to 2 different storms, in this case of same duration 4 hours but different intensities. So obtaining the unit hydrograph for a gauged catchment is therefore not very difficult if we have the required rainfall available and corresponding runoff also available. So we can first separate the base flow, obtain the DRH. From the DRH we can obtain the UH depending on whether we have a single storm or whether we have complex storms, and then using that 4 hour unit hydrograph or whatever duration we want, using that duration, then we can obtain unit hydrograph for any other duration by using S-curve or superposition. But suppose we don't have a gauging station available, that means we don't have a DRH available to us for any given ERH. In that case, we go for synthetic unit hydrographs in which we use the geometric parameters of the catchment, for example, the length or length to centroid, the slope, and so on. And using those geometric parameters, we can obtain a unit hydrograph which is not based on any observed runoff, but it is just a synthetic hydrograph. So we will look at the Snyder's method. So synthetic UH means we don't have any data available for the catchment. Snyder's method is the one which is Snyder has proposed, and there are some equations which are given by Snyder. For example, he said that if we have a catchment the length of the catchment is L along the stream, centroid of the catchment is somewhere here, and the length to centroid is LC. Area is A in kilometer square. Lengths are typically, although in the original Snyder method they were used in miles, but we will be using kilometers. So L and LC would be in kilometers, A will be in kilometer square. So what Snyder has in his synthetic hydrograph, he has related the characteristics of the hydrographs. Suppose this is the duration of the rainfall, TR, effective duration, from the center of this rain to the peak. He called the lag as TP. So Snyder related this TP with the catchment characteristics, and he said that this TP is standard value, some constant, into LLC to the power 0.3. And for this standard lag, the duration TR is TP divided by 5.5. So if we have the data available for, let's say, a gauged catchment, so in this case we will take an example. CT is a constant which depends on the basin properties. In this case we will assume that there are two catchments. One is gauged. So catchment 1 is gauged, and gauged catchment means that we can obtain the unit hydrograph for this easily. Catchment 2 is ungauged. So using the data, but they are very similar. The assumption has to be made that they are very similar. That means whatever the value of CT is for this catchment, same value of CT can be used for catchment 2. For the catchment A, the data is given as area 60 km square, length 15, and up to centroid 9. So this LC is 9, L is 15, and the area is 60 km square. A 4-hour unit hydrograph for the first catchment has been obtained because it is gauged. So we have obtained the unit hydrograph. The peak is given as 15 meter cube per second, and time to peak is 4 hours from the center of the rainfall. So this TR is 4 hours. So center means that we have 2 hours, and then further 4 hours from that. So TP is 4 hours from here and 6 hours from the time 0 of the starting of the rainfall. So TP in this case is 4, and the duration of the rain is 4 hours. So we can see that TR and TP do not satisfy this relationship. So this 4 hour is therefore not a standard duration as far as Snyder's definition is concerned. So we would have to find out the coefficient CT and CP, knowing that this T, TP and TR are not standard values. And in that case, Snyder has given a relationship. If TR is not a standard, then for any other rainfall duration of T capital R, Snyder has given this relationship, which can also be written as because this TR we have seen is TP divided by 5.5. So let's use this relationship to obtain the value of CT for the catchment which is gauged and for which unit hydrograph is available to us. The other relationship which has been used to obtain the discharge, the peak discharge, is given here, in which the peak discharge QP is given as CP into 2.78 A over TP. So CP is also another constant which we can obtain for the catchment 1. So our aim would be to predict the value of CT and CP from this catchment, and since they are similar, we can use the same CT and CP for this catchment and predict the value of peak and time to peak for the second catchment. So the computations are shown here. For the gauged basin, TP star is 4 hours and TR star is 4 hours. Star denotes the value for the gauged catchment. The standard lag, as we have seen, TP can be obtained using this equation. As 22 by 21 TP star minus TR star by 4, and comes out to be 3.14 hours. So this means that for the given basin, the standard lag should be 3.14 hours, and since we know the equation for standard lag, we can obtain the value of CT as standard lag divided by L star LC star to the power 0.3. For the catchment 1, L is 15, L star is LC is 9. So we have 15 into 9 to the power 0.3, and TP is 3.14 hours. This gives us a CT of 0.72. Similarly, since we know the peak discharge for the catchment, we also know the peak lag, the basin lag, we also know the area. We can find out the CP value as 0.36. So these two values are now known to us, CT and CP, and using these values we can derive a synthetic value of the unit hydrograph for the catchment 2 which is not gauged. And for that, let's assume that we want a 4-hour unit hydrograph. So given a 4-hour unit hydrograph for catchment 1, we want a 4-hour UH for catchment 2. This 4-hour again is not the standard duration as far as Snyder's definition is concerned. So we can write this equation where CT into LLC 0.3, this is the standard lag, 21 by 22 plus TR by 4 should be equal to 1, the basin lag for this corresponding rainfall of 4 hours. So this gives us a lag of 4.56 hours. We can see that the time to peak, or the lag in this case, was 4 hours. The area was 60 kilometer square. Since this is a larger basin, 100 kilometer square area, L and LC are also larger, we expect that the lag will also be larger. So in this case, compared to 4, we get a lag of 4.56 hours. The peak discharge is obtained, CP we have already seen from the previous basin as 0.36, CT we have already seen as 0.72. So using these values of CP and CT, we get the peak discharge as 21.95 meter cube per second, area of the catchment 100, and TPR of 4.56. Per unit area, the peak discharge per unit area can be written as, since the area is 100, 21.95 divided by 100 meter cube per second per kilometer square. Then to help draw the hydrograph, there are some equations which are proposed. For example, the base, time base of the hydrograph can be obtained by approximating it by a triangle and equating the area to be unit. So TB can be given by 5.56 divided by QPR, and it comes out to be 25 hours. In this case, 25 hours seems to be a little small because we have earlier seen that the unit hydrograph for the catchment 1, which is gauged and is smaller, has a time base of about 40 hours. So this 25 hours seems to be a little small, and we will increase it later when we plot the curve. There are two other significant values. One is what is the width at 50% of the discharge, peak discharge, and what is the width at 75% of the discharge. The equations which are given are W50, which is the width at 50% of the peak discharge, is 2.14 divided by the peak discharge to the power 1.08, comes out to be 11 hours. W75 comes out to be 6.3 hours. It has also been proposed that 1/3 of this should be before the peak and 2/3 after the peak. So out of this 11 hours, 1/3 should go before the peak, 2/3 after the peak. Similarly for this. So using this data, time base, W50, W75, peak discharge, the lag 4.6 hours. Using all this data, we can plot a few points and then join them by a smooth curve to obtain the synthetic unit graph. In this case, 0 and 25, these two are based on the time base of 25 hours. Then we have the peak, this should be 4.6 hours from the center of the rain. Center of the rain is at 2 hours because the rain actually is occurring up to 4 hours. And from the center, this is 4.656 hours based on the value computed here. So this total should be 6.56 hours. Now the peak is also known to us. Let's say that this is 22 roughly, because the value which came out from the calculation is 21.95. So we can say that this is peak is 22 at 11, which is 50% of peak, and then 16.5, which is 75% of the peak. We know that this total width is 11 hours and this is 6.3 hours. Half of this, 1/3 of 6.3, 2.1 goes here and 4.2 goes here. So knowing the peak, we can obtain these 2 points. Similarly, from the peak, 11 by 3 here, 22 by 3 here. So we can obtain these. So 1, 2, 3, 4, 5, 6, 7 points are known on the Snyder's curve. The area under the curve will be 1 centimeter of rain over 100 kilometer square area. But if we look at this curve, it's not smooth. So what we will probably do in most cases is join it by a smooth curve. And also we have seen that 25 seems to be a little small, so we would like to have it increase up to 40. So we will try to make it such that the area remains similar. So whatever area we have excluded here can be included here and so on. So we can get a smooth curve based on neighboring catchment, a similar catchment, and we can obtain this synthetic unit hydrograph. So the synthetic unit hydrograph can be derived for a catchment for which we have geometric or geomorphological data available, and we can estimate the values of the coefficients CT and CP for a similar catchment which is gauged, and therefore we can obtain those values from a unit hydrograph derived for that other gauged catchment. Using those values of CT and CP, we can estimate the synthetic unit graph for the basin which is not caged. But this synthetic unit hydrograph, or whatever hydrographs we have discussed till now, they are of a particular duration. That means that we can use them to predict the DRH for a rainfall of the same duration, and of course this duration can be changed. We can derive a rainfall runoff relationship for a different duration of rain by using a unit hydrograph for that particular duration, and we have already seen that given any duration of unit hydrograph, we can derive any other duration hydrograph easily using S-curve or using superposition. But sometimes the rainfall which occurs may not have a uniform intensity. The intensity may be varying quite a bit. For example, we may have, let's say, a rainfall which has intensity like this. In this case, making the assumption of a constant intensity over finite intervals may be valid, but it may not be very accurate. So in this cases where the intensity varies continuously with time and uniform intensity assumption cannot be made, we should look for a unit graph which corresponds to instantaneous rainfall, and this is known as the IUH, or instantaneous unit hydrograph. We have seen some of the methods. For example, we have seen the Nash model, in which the instantaneous unit hydrograph, which is defined as the instantaneous unit hydrograph T versus Q, the rain which causes, so this is the UH, the effective rainfall for which causes this instantaneous unit hydrograph is a rainfall of very high intensity and so very small. Suppose this is delta T and this is intensity is, let's call it 1 over delta T. So the volume of rain which occurs is 1, or the depth of rain into the catchment area. So depth of rain is 1 centimeter, but it occurs at almost 0 times. So as the limit delta T tends to 0, it becomes instantaneous rainfall of very large intensity, very small duration, in such a way that the depth is 1 centimeter. In other words, the entire 1 centimeter of rainfall occurs instantaneously at the catchment, and because of that it causes a runoff like this. We have seen that Nash model is one of the models which is used for instantaneous unit graph calculation. The equation which is used for Nash model comes from linear combination in series of reservoirs. So we have a reservoir in which there is some rain here, some outflow goes into second reservoir, there is some outflow which goes into third reservoir, and so on. So n is the number of reservoirs and k is a time constant. In this case, we have taken, to illustrate the Nash hydrograph, n equal to 4 and k equal to 3 hours for a catchment of area 60 km square. This U value is an ordinate which is expressed in per hour, and what it really means is centimeter per hour per centimeter rain. So since we are saying that this is unit hydrograph, it will have 1 centimeter of rain, therefore U can be written in terms of centimeter per hour. And that is what we have done in this figure, in this table, which shows the value of U computed from this equation with k equal to 3 and n equal to 4. The ordinates are expressed centimeter per hour here, and then based on the catchment area we can convert it into meter cube per second. These ordinates can be seen here with the peak occurring at about 10 hours of almost 12 meter cube per second, and the plot of the IUH, this indicates that over a catchment of 60 km square, if a 1 centimeter rain occurs at time t equal to 0 instantaneously, then this would be the resulting hydrograph with a peak of almost 12 meter cube per second. And as we have already seen, that this IUH can be used to obtain the DRH because of rainfall of varying intensity by using the convolution theorem. So here we would look at some uses of this IUH. Suppose we are given the IUH and we want a 2-hour unit hydrograph derived from the IUH. Now, since the IUH represents instantaneous rain, if we take any time interval delta t, the average of these two ordinates will give us the ordinate of the unit hydrograph. Suppose this is 2 hours. Then if we want the 2-hour unit hydrograph, the value of 0.7 here is the average of these two. Mean of 0 and 1.4 will give us 0.7. Similarly, the ordinate of 2-hour unit hydrograph at 4 hours would be the mean of 1.4 and 5.8, and so on. So all the ordinates can be obtained in such a way. So this 0.13 is the mean of 0.16 and 0.1. So the 2-hour unit hydrograph can be derived. This is the 2-hour because the difference of these times is 2 hours, and it can be plotted like this with a peak of about 12 meter cube per second. Now once 2-hour unit hydrograph is available to us, we can use this to obtain S curve. So suppose this 2-hour unit hydrograph is available to us. This can be obtained from an IUH, or it can be obtained directly from if we have a gauged basin. Suppose we have a 2-hour rain, we can get the corresponding DRH and get the 2-hour UH from there. So from IUH also we can obtain the unit hydrograph for a given duration. But what we would look at is, for a given hydrograph, how to obtain the IUH. So suppose directly we know the 2-hour UH. Based on the 2-hour unit hydrograph, we can obtain the 2-hour S curve. So those values are shown here, and as we have seen, the relationship between the ordinate of the IUH and this is the S curve ordinate. The S curve looks like this. What this equation tells us, that the slope of the S curve at any point ds by dt divided by the intensity of rain will give us the ordinate of the instantaneous unit hydrograph, because S curve represents the rainfall due to infinite value. If we shift it, suppose we shift it by delta t, and suppose this is delta S. So when we shift it by an amount delta t, delta S represents the Q value due to a rain of intensity I for period delta t. So this is what delta S represents. It represents, since we have shifted by an amount delta t, it represents the amount of runoff which occurs because of two rains, one of intensity I continuously, the other of same intensity but shifted by delta t. So any change here, delta S represents the Q due to intensity of I, period of shifting of delta t. And as delta t becomes 0, delta S by delta t will tend to ds by dt. So this I rainfall for a period delta t means the volume is I delta t. Since we want a volume of unity, delta S over I delta t will give us the unit hydrograph, instantaneous unit hydrograph ordinate U. So U will be equal to delta S divided by the volume of rain, which is I delta t, and therefore in the limit delta t tending to 0, delta S by delta t will tend to ds by dt, and therefore U will be 1 over I ds by dt, which is what is written here. So once we derive a 2-hour S curve, we can obtain the slope of the S curve at any point divided by the intensity. In this case, since it is a 2-hour S curve, I will be 1 by 2 centimeter per hour. So the procedure is obtaining the S curve first. S curve, of course, is very easy to obtain because once you have the 2-hour UH, we have already seen how to lag them by 2 hours, add them up, and then get the 2-hour S curve. So in this case, by doing that, we have obtained the 2-hour S curve ordinates. Maximum value of 83.35, which corresponds to intensity half centimeter per hour over an area, which in this case is given as 60 kilometer square. So area is given as 60 kilometer square. If the intensity is taken as half centimeter per hour, it will result in an ordinate of 83.35 at the end, or the asymptotic value. So we can plot this S curve, and as it is shown here, this is the 2-hour S curve. If you look at the slope of this S curve, initially the slope is almost 0. At the end also it is almost 0 because it attains a constant value. So the slope is 0 here, increases, then there is a point of inflection. After that it will start decreasing, and then ultimately the slope will become 0. And the instantaneous unit hydrograph can be obtained as 1 over I, which in this case will come out to be 2, since I is half, into ds by dt. So the slope of this we can obtain either numerically, so we can use central difference, or we can try to fit a curve and then take the slope, linear interpolation or quadratic interpolation. Here what we have done is, suppose we want the slope here, we have used the central difference approximation. So the slope will be obtained by joining the two surrounding points and divide by delta t. Delta t in this case, since we have every 2-hour intervals, delta t will be 4 hours, and delta q will be the difference in the next q and the previous q. So using that, we have here the value of 0 and 0.7 and 4.3. We want to find out the slope at this point at 2 hours. So what we will do is take the difference of the two neighboring points. The next point 4.3, previous point 0. So 4.3 divided by delta t, which is 4, gives us a slope of 1.08. Intensity, as we have seen, so the IUH ordinate is 1 by I ds by dt. I is 0.5 centimeter per hour. ds by dt we have obtained, so 1.08 is 4.3 minus 0 divided by 4. Similarly 2.88 is the difference of 12.22 and 0.7 divided by 4, and then IUH will be multiplied by 2, so this is into 2 will give us 2.15. Similarly all these values are multiplied by 2. So in this way, given a 2-hour unit hydrograph, we can derive an IUH for that particular basin, and in this case the IUH turns out to be like this. We can join them smooth with a smooth curve, and this IUH comes out to be very similar to the IUH which we had used to derive the 2-hour UH. So this was the IUH which we had used to derive the 2-hour UH. Then we use the 2-hour UH to derive the S curve for 2 hours. So the 2-hour UH is given by this curve. Using this 2-hour UH, we have derived the 2-hour S curve, and then from this 2-hour S curve we can obtain the IUH, which should be similar to what we had started with, but this just gives an idea of how to obtain an IUH for a given unit hydrograph. Typically duration of 2 hours we have taken, but 1 hour duration would be better. More than 1 hour taking the slope by this finite difference approximation may not work very well, but for 1 hour it should be quite good. Less than 1 hour is okay, but 2 hours we have taken, for example, it may not be very good from accuracy point of view. So we have looked at some of the techniques in this case to obtain the unit hydrograph for a duration which is not a multiple of the given hydrograph duration. We have also looked at if a catchment is not gauged but a similar gauged catchment is available to us nearby, how to obtain the unit hydrograph synthetically using the Snyder's method. Then we have seen that if the rainfall is not of uniform intensity over the whole period, if it is varying widely, then we may not be able to use the unit hydrograph theory, because that assumes a rainfall of constant intensity for a given duration. In that case, we can go for instantaneous unit graph, which can be used to obtain DRH for any varying rainfall by using the convolution theorem. The IUH can be derived based on Nash model, which we have seen is based on a gamma function, and it's a combination of linear reservoirs in series. There are other methods also of obtaining IUH. We have seen one method which is based on obtaining the S curve for a given unit graph and then taking the derivative of the S curve to obtain the unit hydrograph IUH ordinates. There are some other methods also. For example, there is a Clark's model in which we use what is known as time area diagram. So we divide the catchment area into sub areas which all have almost same time of travel for reaching the outlet point, and then these different areas can be plotted with time and we get a time area diagram, and that time area diagram we can use to obtain the IUH, because we assume that instantaneously the water is falling over the entire area, so it will have some lag time for reaching the outlet, and those time area diagrams can be prepared and they can be used for IUH, but we will not discuss them here. So we have looked at the two methods, which are Nash model and then using any other UH of preferably a short duration, for example 1 hour duration or 2 hour duration, we can obtain using the S curve. From the slope of the S curve we can obtain the IUH.